college seniors who are interested in graduate school in science, math, and engineering to Boulder for a Thursday, Friday, Saturday to showcase our graduate programs, let them meet faculty within the department that they're interested in. They'll pre-select who they'd like to meet with ahead of time. They'll have laboratory tours, a campus tour, and there'll be workshops on how to competitively complete a graduate school application, so it'll boost in addition. So we're trying to recruit more, we're trying to make them more successful at getting into UC Boulder. So we're trying to make faculty aware of this program because it is brand new. We haven't done this yet, and we're going to need the support of faculty to carry it out, both in terms of the willingness to meet with students, to help out with some of the workshops that we have planned, and so on. So does anybody have any questions? I do have some.
Well, you could, if you send us a PDF,
okay.
I'll just send it around.
Oh, okay.
So is it all science departments? Are you targeting any particular set of disciplines, or?
Well, we've gotten so everybody's chipped in a bit of money, and so College of Engineering, for example, is giving us $3,000. So that $3,000 will pay for students to come to College of Engineering. CIMB has contributed $3,000 again, but the bulk of the funding, more than $10,000, is coming from us in the graduate school. So we'll just be where the competitive applications are. So the students that we invite to come will be selected by the departments, by the admissions committee in departments. We're not going to select them.
So these are people who are applying in the fall?
Who will apply.
They will apply in the fall.
Yes, this is to encourage them to apply by showcasing their programs here and by helping them prepare competitive applications. We can review in October. Yeah, so it'll be
Oh, okay.
yeah. So it's a chance for them to just come and see. So a lot of larger schools have these in place right now. We just haven't. Berkeley has told me it's their biggest benefit of recruiting about. You get graduate students. So it also is helpful for faculty who are preparing training grant proposals that have a whole university plan and we can put on the table. That's a really easy thing that a faculty member can include funding for a proposal. It's very inexpensive, $1,000 a student.
Who are you targeting? I know you're targeting seniors, but are you targeting seniors in the state of Colorado?
National.
National?
Yeah.
Okay.
We tend to draw our underrepresented minority doctoral students from Texas, California, and Puerto Rico. That's the very general statement. They come from all over, but that's where most are. But we'll target everywhere. And I have a lot of national networks to be able to do that.
Any other questions? Anybody? So we'll send out the PDF.
Okay.
And then what we'll do is everybody who gets it should send it around and keep the bushes a little bit. So you're going to do it in October.
Yeah. It's either going to be October 13th or 15th or October 20th or 22nd.
So the ISTEM mini symposium is the 10th, right? Okay. So we'll conflict with that.
It doesn't conflict with that.
Oh, we go. I mean, it would be even interesting to take people to the MCDB retreat if you were targeting people in MCDB.
And we'll need faculty support to help run the panel and interact with students so they don't want to go on. That's the main concern.
No, I mean, it makes sense.
But if you're interested in being involved in that way and helping to recruit students to programs in your labs, you contact our forms of putting together those programs and let the students know how to get.
Sounds good. I mean, personally, I'm a little skeptical about how many labs in the department will have funding, but we'll see. It's not a good time to go into biomedical science.
What do you mean to encourage people to come to practice?
That's their decision, right? We're not forcing them to practice.
No, that's phase 2.
We're going to go in and kidnap people and take them to graduate school.
We'll start with this.
Put little collars on their ankles so they can't leave the building, stuff like that. Okay, so, and if you wanna bug out, that's good. Okay, Kim.
All right. Hi, everybody. My name is Kim Trenbath. I've been with the Deaver Group for a couple years now, and my presentation is a team approach to transforming atmospheric science laboratory exercises. First, I want to go over the objective of this presentation, and that is to share the curriculum development experience and the project outcomes. So what I'm going to be doing here is I've worked on a project where a group of people have developed laboratory exercises and implemented them into the undergraduate curriculum. And I'm going to kind of talk about how we did that and then talk about the successes and so on and so forth. So outline, first I'll talk about lots of different backgrounds of ATOC and myself and the project, and then the curriculum development process. I'll give an overview of the radiation lab exercise, and then how we assessed this radiation lab that we developed, and then I'll give an overview of the precipitation lab that we developed. So we developed 2 labs that I'm going to talk about here, and then we'll have a short discussion. So some background. The Department of Atmospheric Sciences, which is my department, was founded in 2005, and I'm actually a graduate student in that department, and I've been here since 2006. Before 2005, it was actually a program instead of its own department, so it's fairly new, and I guess I've been there for the majority of the time that the department's been around. The department has 15 core faculty, and a lot of those faculty I would consider pretty interdisciplinary. And when I talk about atmospheric science, we're not just a meteorology department. We include people who do climate research, oceanographers, a lot of graduate students, and some core faculty are in the chemistry department. I said atmospheric science because a lot of professors do work with atmospheric dynamics. I slapped on air quality here because I did my master's in air quality research with people in mechanical engineering. So you can definitely be in my department and be doing air quality research. And then perhaps atmospheric science education. I'll be the first graduate with an interdisciplinary degree with a PhD from the Department of Atmospheric and Oceanic Sciences. So maybe in the future we might have some more ATOC faculty doing some atmospheric science research. And I just want to say, like, throughout this presentation, feel free to ask me any questions and interrupt me if you'd like me to describe something a little bit more.
My understanding is that you don't have an undergraduate major.
Oh yeah, that's correct. So yeah, we don't have an undergraduate major, we have an undergraduate minor, and a lot of our students, such as myself, are graduate students, and there's some students who get masters, but most of the students are PhD students in the program.
So undergraduates interested in atmospheric sciences will usually be majoring in chemistry, physics, geology, or something
Exactly.
like that, but will take a minor in your department.
Exactly, and the people who end up taking a minor end up coming from a variety of majors, a lot of environmental studies, and some people as far as journalism who want kind of the atmospheric science background, which is definitely a little bit different. And I'll go into the, I guess, draw from the different majors shortly. So the reason why I'm doing this presentation is because 2 professors, Dr. Peter Paluski and Dr. Katja Friedrich, were awarded a grant from the NSF called an Atmospheric Science Laboratory for Undergraduate Education. And they were tasked, well, their grant proposal involved establishing a rooftop science observatory and also establishing a place where people can access that data online. And that place is skywatch.colorado.edu, which is here also. And so all this data, I'll go into Skywatch in a second, but the goal was also to have this publicly available and be able to use this in atmospheric science classrooms at CU and probably across the rest of the state and possibly the nation. And then the third piece is to develop a local instrument-based curriculum, so to integrate these instruments into the ATOC curriculum in some form. So here's what the Skywatch Skywatch Observatory looks like. So on the right is a picture of what the Skywatch Observatory is. It's actually a platform on top of Duane Physics. So not the Duane Physics Tower, but Duane Physics Building. So it's about the 4th floor of Duane Tower. And it has various atmospheric science instruments on it, primarily radiation instruments and precipitation instruments. And all the data, once it's downloaded into the server, can be accessed online at skywatch.colorado.edu, and that's the second screenshot that I have here. And there's archive data, and there's information on there about the different instruments. So some of the instruments that we have up there are a pyronometer and purgeometer, 2 instruments that measure radiation, and I'll talk about those a little bit later. A stylometer, which measures cloud base height of different levels of clouds. So it has the capability of measuring the cloud bases for three cloud, levels. A sun photometer, which tracks the amount of optically active aerosols in the atmosphere, such as particulate matter. And a solar spectral flux radiometer, which charts out the solar spectrum that's it's receiving from the sun. A pluviometer, which measures precipitation intensity. A distrometer, which is another instrument that I'll talk about later, which also measures precipitation, but includes the size and velocity of the precipitation. And then micro rain radar, which measures rainfall rate, liquid water content, and drop size distribution. So I said I would talk about a couple instruments later, and here they are. There's the pyronometer and purgeometer, and the reason why I'm highlighting these are these are the ones that we actually showcased in the curriculum that we developed. So that's why I'm showing you a little bit more about them here. The pyronometer is the one with the dome on it, kind of towards the right in the picture that you see in the middle of the screen, and then the purgeometer is the one on the left. The pyronometer generally measures what you would consider visible light, and actually the wavelengths between, specifically the wavelengths between 300 and 2800 nanometers, and the purgeometer, sometimes casually considered measuring the infrared from 4500 to 42,000 nanometers. And so the output that you're going to see online from these 2 instruments will be those 2 charts underneath each. And so you can see with the pyronometer, you can get kind of the solar intensity as the sun goes up and then the sun goes down. And then you can see a little bit of noise in that experiment, or in the, it's not noise, excuse me, you can see a little bit of it's not a perfect parabola, and it's because there's clouds there above it. And then on the other side, you're seeing the purgeometer readings. And then the distrometer, and this is, measures the precipitation, and it actually classifies the precipitation, and it measures the size and velocity of the precipitation. And this is what it looks like. So it uses a laser to make those measurements. So a little bit about background about ATOC. So there's 3 major, there's 3 classes in ATOC that draw a crowd of undergraduate students here at the University of Colorado. And there's a few reasons of that, and you guys can be you're probably familiar with this. First of all, there's ATOC 1050, Weather and Atmosphere, and then that's a 3-credit class. ATOC 1060, which is called Our Changing Environment, which is focused on climate change, and that's 3 credits as well. Both lecture hall classes normally taught by a professor, sometimes tenure track, and sometimes taught by a instructor. And then we have the ATOC 1070 Weather Laboratory, which is managed by the instructor for the department, the senior instructor, and it's taught by graduate students, so graduate TAs, and that's 1 credit hour. And ATOC 1050 draws a lot of your non-science major classes because around campus it has a rumor of being the easy science, perhaps because it's, I guess, an earth science, and people can see the earth science. Now there's a caveat to that, because sometimes when you're talking about climate change, you're talking about chemistry and physics, and the students will be in these classes and they don't have chemistry and physics. They never took it even in high school. So a lot of the challenge is talking about the science in front of students who don't have this background. So that's a big challenge for some of the professors in our department. Also, these two classes, the top two, are part of the sequence for the natural science core in arts and science, and then the laboratory also satisfies that core. So we get, so ATOC 1050 gets it's 2 classes every semester, and it gets 301 and 200 in the next. And ATOC 1060, I think there's 2 classes of that each semester, and it has a capacity of 200, but they get about 150 in both sections. And then ATOC 1070, there is about 14 sections. We actually got, I don't know, it's probably familiar with you guys, the number of sections got cut for our department, so I'm making some estimates here. There's about 18 students in each session, and that actually might be increased because now we're increasing class size because of the funding here. So, and then on the picture to the side, you can see some of the students doing some of their experiments. And actually, these students are actually on the back of Dwayne Field measuring, tracking a wind balloon, or excuse me, a weather balloon. Oops, that's not the right thing. Hit the wrong button. And that's just part of their labs. So the one I'm going to focus on here is the ATOC 1070. And when we were determining which class to implement the instruments in a curriculum based on the instruments, we picked the ATOC 1070 lab because it's naturally the most intuitive one to put an instrument-based module into. First of all, the laboratories are based just like very similar to laboratories across campus. They are all standalone laboratories. They don't continue throughout the whole semester. Students come in, they meet once a week, they come into class, they do their laboratory and produce, they gather data, analyze results, and produce conclusions within that time frame of 2 hours. And so they have about 12 labs sessions throughout the semester. And those lab sessions generally focus on the following topics: moisture, radiation, hurricanes and winds, weather balloon tracking, gas law, and severe storms. So I have highlighted here the moisture and the radiation because these are the 2 topics that the labs that we developed, they are going to fit into these modules of the lab, if you will.
Now, are the lecture and the lab courses co-requisite, or is one
They are.
prerequisite for the other?
Thanks for asking the question. They're not a co-requisite. They're both standalone courses, so a student who registers for one doesn't automatically have to or have to enroll in the other. So you register for both, and we do have a problem with students registering just for the lab and not having the ATOC 1050 background, even though ATOC 1050 is actually a co-requisite of 1070.
So if you had to sort of summarize what a person needs to know to succeed in these classes, what would it, I mean, before you teach them, what would it be?
Oh man, that's a great question.
We can answer it later.
Yeah. In a weird way, students make it through without having the background knowledge.
So do they need math? I mean, do they need to be
They
able
do
to
need to know a little bit of algebra, but honestly, like, the algebra is so handheld in some of these courses. For
So
example, when we
they're-
calculate the slope, there's an equation in Excel that already does it for the students.
Oh, okay.
So I guess that's a good point. The existing lab was developed and kind of tweaked throughout the years because the instructor noticed that students really struggled on little things such as algebra, and they didn't want to make that the emphasis of the lab. So eventually they started making the equations automatically pop up in the Excel program once you typed in your data. So there is some data analysis where you're making your own graphs, but a lot of it was just straight up, here you type in your data, boom, here you go. Now think about it, because the instructor was really trying to keep towards the atmospheric science side and away from those tools like algebra and what is the slope of the y equals mx plus b equation, because that was really difficult. Like, I've had students, I taught this lab many times, and I had students like, what's the slope? I was like, okay, well, all right. Anyway, so the curriculum development process. So this, I think, I would say it's a unique approach, and maybe you guys can shine some light as to how unique I think I am actually being here. Because what we did is when we had this, so let me step back and say I managed this development approach, and that's why I'm doing this presentation in front of you today. And even though I managed it, we tried to involve a lot of the people in our department. So it wasn't me making all this curriculum or just one person. It was a lot of cooks in the kitchen, but that was a challenge, and we actually were able to get through that. So we had on the team the 2 professors, a senior instructor who managed the labs, a professional research assistant who actually managed the Skywatch laboratory, and then about 8 graduate students. And the majority of those graduate students were current teaching assistants. So they all had teaching experience, and a lot of them were very interested in continuing on and becoming professors when they're done with CU. And the goals for this process were to incorporate the instruments, of course, and incorporate scientific inquiry. So we wanted to move away from some of those, like, what we call cookbook type labs, where you type in the numbers and here's your answer, but I don't really know why it's here, and we copy off my friend type of deal. So we really wanted students to think about why they were getting and seeing the things that they were seeing. And then the next thing was we used top-down lesson design. And this is sometimes called, I call it top-down, I just said it here, but sometimes people call it backwards planning. Where instead of saying, oh, hey, I have this really cool activity I want to do in my lab, you actually think about what is your essential question first of all, and then you step down from there. So essential question, develop your lesson objectives, go down to your assessment before actually making your learning plan. So that is the step. Those are the steps that we actually followed for this team. So in the development phase, this is kind of a schematic about how it worked. So first we all met as a team, and then the professors actually generated the high-level ideas for the lab. And then we passed it down, and then they passed it down to the team. And when I say team here, I'm talking the graduate students, the lecturer, and the research assistant, who actually tweaked it and added some of those inquiry ideas into the lab. And so what you're doing is you're merging those high ideas coming from the professor, like the actual technical stuff that they want the students to know, with some of the I guess, people who are down in the trenches and the teachers who are developing their pedagogy. So that's where the merging kind of came in, where we were developing this lesson, and then the lesson would go back and forth between the team and the professors a couple iterations.
How were you facilitating the collaboration?
So the team would meet to do that. So we did have meetings, and they were, they definitely took a little bit of time, but the TAs they were eventually going to teach this in their laboratory, so it was definitely worth their time. Yeah.
How long did sort of rough timeline for each of those boxes? How long did you spend doing each of those boxes?
So let's see. Kickoff meeting would be like an hour and a half.
Well, I meant, like, does this happen over the course of the semester, or is this?
Oh, you mean the whole thing? The whole thing. If you want to do it really quickly, you could probably do it in a couple weeks. But it probably took us 2 months to do this. I mean, because there's some spaces. Because when people were just like, okay, I have to do this, but I have to do other things.
Yeah, I think 2 months is pretty short.
Yeah. Yeah, I guess the team was pretty well, the graduate students were pretty well focused, and there was a lot of work that came out of their team meetings. And a lot of, kind of divide and conquer, this graduate student did this person did this, and then everybody came together at the end.
The graduate students, they've had experience teaching, but were they actually TAs for the course while they were doing this
Yes.
exercise?
Yes, that's a great question. So they were first year graduate students,
Okay.
and it was second semester when we developed
All
this.
right.
So they had already taught the lab first
First semester.
semester, and they were teaching it second semester, and then they developed this, and they already had that knowledge from teaching it the prior semester. And I can say that all of those graduate students actually got the GTP certification. They were, so we had people who were really interested in teaching. And it was optional, you didn't have to do this if you didn't want to. I bought everybody dinner, but
Yeah,
that's
so
fine.
sort of thinking what incentives do the graduate students
Um,
have to participate besides,
I think camaraderie. I think they were just.
wonderfulness?
Yeah, that's a good question. I think.
First-year graduate students have a lot of demands on their
Mhm.
time, and sometimes don't feel that they have the time to get involved in something like this. So-
Right. I think since they were just interested in teaching, so this was actually something that is dear to them, and they definitely
But
wanted to.
also, was there pretty clear statement from the department that this is a worthwhile thing?
I think they knew that once they developed it, it was going to be in the lab and that they had ownership of it. I think a lot of them did want to change a couple of the exercises in the lab after teaching it the first time.
Okay.
And so this was their opportunity.
So, what did most, so I don't understand APOC, right? So what did
Okay.
most graduate students in APOC end up doing?
Okay, so you mean like for research or when they're
Or
graduated?
When they grow up, adults?
When they become adults? So you have some professors and you have a lot of, you work at NOAA or NCAR.
No, but
So they do
that would be
climate.
so would they be a lot of teaching in their job, or would there be a lot of interacting with the public in their job, assuming that NCAR and NOAA are still open next week? Do they do a lot of outreach, or do they do any research?
Let's see.
It would be interesting. It would be interesting to know.
Traditionally, the graduates have done lots of research, but things are changing in our department. I came in and I was like, I really want to do teaching, and I think my peers, because I was part of like a large group of graduate students, and there's 15 of us, and I heard a lot of my peers saying I want to do research, but now I'm hearing a lot of my peers say I want to teach. So things, it varies, and there's like pros and cons to both, I think. I actually envision, when I get done, I want to be, I want to be teaching. Like, I think I always want to be teaching at least one class. So,
But so can you, it'd be nice to know, so that people go so they go to small colleges, big universities, do they, where do they go? You don't have to do that right now, but I'd be really interested to know.
Right. Well, remember, our department's pretty small, and a lot of them go to research organizations throughout the world, actually. That was in the past, but we don't know what's going to be happening like now. Like some people have gone to be professors in smaller liberal arts colleges.
One
Yeah.
sort of point of background is that,
Oh wait, sorry.
go ahead.
Well, I was just wondering is this a revision of an existing lab, or did you throw out the existing lab and just say, okay, we're starting from scratch now?
It was pretty much, there is a lab that we compare them to this. So we had two labs. There's a radiation one. The radiation, we wanted to throw out a lab. In the end, we ended up keeping both labs. So it wasn't, there was iterations in that process also. So I would say this was kind of like starting from scratch, but people had background knowledge and expectations going into it, so you can't really say you have a blank slate. Okay. Sorry. Okay. So then, after we developed this in spring 2009, so early in the semester, we actually piloted this in the TA's classes of the same semester. And the way we did this is a lot of the TAs taught two sections of the laboratory classroom. So we found a lab to compare the newly developed lab with, I guess. And it wasn't a perfect comparison, for example, meaning that the learning goals for both of them were not exactly the same. But I went through this, I thought that this would just be something to do just for the sake of it, because we were planning on replacing some of the old labs with these new revised laboratories. So the process was we pre-assessed with the assessment. Both the instructor taught an old lab and a new lab, and then we post-assessed with the same assessment, which was an open-ended assessment.
Meaning that they wrote something?
Mm-hmm. Right. And then at the same time, there was a rubric for evaluating each person's assessment, or each student's assessment. And then after we did the pilot phase, there were some revisions that we needed. So revisions, the second pilot was done in the summer. of 2010, and then finally in the fall of 2010, these were implemented into the curriculum. So these 2 labs got implemented into the laboratory curriculum. So now let's talk a little bit more in detail about the radiation laboratory exercise. So this lab involved, okay, so I was talking about the pyranometer and the purgeometer before. There's a picture of them here. And what we actually did was we had one that's on the roof of Duane, and the data is being constantly downloaded onto the Skywatch website, or onto the server, and then you can access it from the Skywatch website. But we have a second set of those instruments. So in class, the students were able to play around with those instruments. So they would shine a light on both of them and see what the reaction or response was, and they would, put their hands over them and they saw the response from the purgeometer versus nothing from the pyranometer. And so they could do all those types of things. And then they were able to experiment on their own. And before they had come to class, the students were supposed to take a weather log, and so they looked at the data on their weather log and compared it to the data that Skywatch had recorded. So they do a comparison there. And then they calculate the emissive temperature and the altitude calculation of the cloud heights. And finally, they extrapolate what they learned in this lab to like a bigger picture, meaning that we wanted them to understand how the greenhouse effect works, and by using these instruments. And so we asked them questions like that in their conclusion. And as I was saying before, some of these objectives for the new lab were not the same as the old lab, but when you actually look at these, they're somewhat similar. And so new lab, compare visible infrared radiation at day and night, understanding the factors that influence radiation incident on the Earth's surface, so why is there more, understanding the greenhouse effect. And then the old lab, which was understanding of emission and absorption and understanding the impact of CO2, water, vapor, and other greenhouse gases on the amount of radiation in the atmosphere. And one thing I do want to point out is that the old lab for the radiation, they used the students took plastic sheets and used an IR thermometer and took different IR measurements with their plastic sheets, which to me is a lab that kind of does not necessarily represent the greenhouse effect exactly. Like, the greenhouse effect is a very abstract concept to understand, and it's actually taken me a little while to understand it, and so I've thought a lot about how to teach it. And using these plastic sheets still can cause what we call misconceptions. And so, but it's one of those things where, like, oh, here's a great representation of a physical process that happens, but it's actually not the physical process. So these instruments are actually replacing that, hopefully trying to replace that old representation. But at the end of the day, we kept both of them together because that was just the decision of the group. But we'll see what happens if it gets revised again in the future. Okay, so for the assessment, very similar diagram. Actually, there were 25 students who were taught the old lab and 24 students were taught the new lab, so small numbers. This assessment, I'm going to say, take it with a grain of salt. I wanted to do something to look at differences, but I don't think this is proving anything here. The assessment had questions that spanned both labs. For example, how did this greenhouse effect work? Explain the effect of water vapor, CO2, and clouds on surface temperature, and tell me what you know about visible radiation, and tell me what you know about IR radiation.
So I have a question. What would a really good explanation of how the greenhouse effect works look like?
Yeah, that one.
How much physics and chemistry would we require?
I'm not requiring that much.
No, but I mean, if somebody were to ask to do a really rigorous, explanation of how it works, as opposed to a cartoon version of how it works,
Yeah,
what would it look like? I mean, I'm actually just curious about whether it's realistic to expect people going into an intro-level course without chemistry and physics background to be able to understand that.
Yeah, that's a good. I mean, I struggle with that, right? So I generally, the general explanation is that shortwave radiation. So here's like the general generic shortwave radiation. This is what I would expect a student at this level to understand. Shortwave radiation from the sun. The greenhouse gases, they're selective absorbers, so that the greenhouse gases do not absorb that radiation. It gets absorbed by the Earth. The Earth emits radiation, but it's in long wave form, and now that's the wavelength of radiation that the greenhouse gases do absorb. They absorb them, they emit them, and some of it gets emitted up, some of it gets emitted downwards. Therefore, now you're adding, there's more radiation incident on the surface of the Earth. So that's the very
But the point is that you don't have to give a lengthy explanation of why these things happen because they can measure them directly. I mean, this is the way our any assumption of the greenhouse effect before quantum mechanics. It simply is a fact that CO2 absorbs infrared radiation and oxygen doesn't.
right.
And,
Yeah, we're not going that
and we don't have to
far. I mean, I'm probably not the best person to sit there and like talk about it with the professor either. You know, like I'm not going to sit there and talk theoretical.
They can measure the infrared radiation in the daytime and the nighttime, and they measure what they measure.
Right.
And
Right, and like a lot of it comes from when they put their hand over the purgeometer. You hope that they make the connection that there's radiation. Something is there, rather than it doesn't have to just be light. There's a caveat to this. We turned on the light. We had a light source, and the light source also emits IR. So there's a response at both the purgeometer and the pyranometer with the light. So we struggle with that. So that's something that we might. I mean, that would be something to try to change in the future, I guess. Yeah. So.
No, I mean, it's a hard problem, right?
Yeah.
What the resolution is that you're looking for.
Right, and to try to teach it, like on a hands-on way, it's so abstract because you can't actually see those molecules.
Well, but
doing
another
that.
problem, so, I mean, I don't think it's bad, but what do people do, what percentage of these students go on in the major? Or you don't have a major, just a minor?
I would say very small. I mean, I've taught, pardon?
these are mostly non-science majors.
Yeah, I mean, the number of minors that we have is 60. That's a ballpark figure that I've heard, and I'm just, so I think it's around 60, and that's for 4 years.
And the minor.
That's the minors.
And the minor, and that's just, but those are mostly students who are majoring in a science.
That I actually don't know. I don't
That would
know
be
what,
interesting
I
to
think
know.
this, I'm not sure if that's exactly.
Okay, right.
Yeah, I don't know that number.
That's peripheral.
So here's the, so the assessment, the maximum score on the assessment was 17. And here are my results from the assessment. So you can see with the, I have pre-assessment and post-assessment, and then the students who took the new lab are in the purple. And both of them improved, so there's a positive change in both on the average. And the change from the students who took the new lab was higher. However, they started lower and they ended lower. If that makes sense to you guys. Now, I dug a little bit further because I wanted to find out the reasons for the change. So we're looking at very small numbers here, but I just went ahead and threw these students into categories where I categorized them as low, medium, and high. And the low students were the students who originally scored 4 and lower. My medium students were 4 to 9, and the high students were 9 and above. Now, these students did not score 17 out of 17, so these scores are pretty low. The assessment was designed to not really have a ceiling, like a perfect score that you could make, but it does show that there is room for improvement in both classes. And then I classified improvement levels as a moderate improvement, so I had no high improvement. If you had a score change of more than 4 or more points, small improvement from 0 to 4, and then score decreases if you're going down. So here is the categories and the score change. So these numbers here are students that fell within each initial scoring category. It shows the categories, the movement of the category as a whole. And you can see that this, for the new lab, which is on the left side, that the students, there's some big improvements in those students on average. But if you look at the new lab high students, those students went down. And so you're like, well, why are these students going down? Well, the assessment that I gave them was the open-ended assessment, and the students, I actually didn't grade them. Another colleague of mine scored these.
You designed the grading rubric, right?
The grading rubric was
Or
designed. Okay, so the grading rubric was designed by the professors.
Okay.
I had some input, and the actual grader had input. The assessor. I think grading is not the right term to be using when you're talking about assessments for a survey.
We know what you mean.
Yeah. Okay. Yeah. So it was mutual, like a collaborative effort as well. So the students who scored high and went down were the ones who kind of tried really hard on the first one, and they were like, it seemed like they just didn't try as hard on the second one. And I'm not going to say this is the main reason, but I could assume that a reason was because they saw the exact same questions again, and they had done this the previous two weeks prior. So maybe they might not try as hard on the second one.
In psychology, we call that regression to the mean. So
Oh.
there was noise that went into those high scores as well as true knowledge. And then when they took it again, the noise wasn't operating with them but against them.
Oh, okay.
So it's statistical artifact
Okay.
that you would get by dividing the scores that way.
Okay.
Yeah, you might want to dig through your data and look at the variance.
Mhm. Yeah.
And compare the shift in the mean to the variance, and that's so we give you an idea of the noise level.
Okay. Okay. Thanks for the suggestions. And then in the old lab, we see all scores increasing slightly. And then finally, the last question on the assessment, on the post-assessment was, please rate this lab and explain why you rated it this way. And the scale was 1 to 5. And so the new lab was rated 3.9, and the old lab students were rated the lab 3.43. And now this has a little bit of reason to be a little bit. There's probably something other factors impacting this, because I was there when I did class observations for all of both the new and the old labs that were taught. And in this radiation lab specifically, one instructor was like, "This lab is great. I'm teaching you a new lab today, and get excited, everybody." So that probably had an effect on this, but here's the scores at the end. All right, so precipitation lab.
Can I ask?
Oh yeah, sure.
So you didn't really tell us what the actual your learning goals were, and
Mhm.
whether the students achieved them. So all we know is that they did okay in both the labs. And I'm
Mhm.
curious whether they actually did what you really want students who are learning about climate change, who are potentially
Mhm.
going to be voting on issues, what they actually know about.
Right.
That kind of thing.
Right. So the assessment questions. So that's a good point, and I think there could have been a better job. I could have done a better job of, really addressing the learning goals in the assessment questions. But I did. The team really did when the assessment was written. Okay, so caveat, it wasn't validated, but it was directly pulled from the learning goals of both labs. So
Well,
it's
for
not.
instance, did they get what you just said? That is that the wavelengths come in, they change, then they're absorbed, all that. The basics of
Mhm.
the physics of greenhouse effect.
Right. So the first question on the radiation was describe how the greenhouse effect works. And so my description was kind of the rubric that we looked at, and so some of them got it and some of them did not.
And there's also a question of disentangling what they learned from the lab from what they learned in other parts of the course.
Exactly.
Because you have all that information.
Exactly.
Like were they taught it? Were these concepts being taught in a lecture before or
Yeah.
after?
Some of them,
I mean, there's a lot. There's
Yeah.
a lot to kind of decide.
yeah. So students who have had 1060, so there's 1050, 1060, the two courses. So students who had the second course probably were taught the answer to that question: how does the greenhouse effect work?
Doesn't make me remember it though. But
Yeah, but you can definitely see in some of the pre-assessments they explained it very well, and so then they might have, those students were the ones that, if they just didn't do it as a thorough of enough, didn't explain it as thoroughly, then their score went down.
So you gave them the same test both times. And so do you think there's any chance that the students went back and said, hey, I can't remember how that greenhouse effect worked, and outside of class, outside of the lab, looked it up?
Yeah, possibly.
Because, I'm a psychologist, but what we would do is have two versions of the test. And half the people would have, for the pre-test, one version, and the other half would have the other, and then you'd switch for the
Okay.
post-test, so that they couldn't do that. They couldn't already know what the questions were, and then try to study them in advance.
So they would have a whole different set of questions
You
in
had
the
like 6
post-test.
questions instead of 3,
Right.
and they'd be paired, and one of
Oh, right.
And
right.
so, one group would get half of the questions
Mhm.
as a pre-test, and the other half as post-test.
Right.
And it would be switched for the other half of
Right.
the subject. So it's a little harder, but then you don't have that one problem at least.
Right. Right.
But Kim, did they know they were going to be taking a post-test on this topic, or did you just give them questions? I mean, some of it has to do with whether they're expecting to see the questions again, because then they might be like, oh, yeah, maybe I'll try to remember this, even though it has no bearing on my grade, which, might not
Right.
motivate them in that case. But still, if they don't even know it's coming, then they are probably
They
going to
would
be
be
as likely to
curious,
look
you
it
know,
up.
oh, wow,
Right.
Have you
I
taught our
learned about
immigrants
greenhouse
recently?
effect.
Some of them might be, but
I
My
mean, forget
experience
about
is
the
that
test.
when we give students surveys or assessments and they're told that it doesn't contribute to the grade, most of them tend to completely forget about it.
yeah,
after they've done it.
that's
They
been
don't-
our observation certainly, that they don't tend to care too much when they don't think it's going to affect their grade. Not that they never think about it again, but that they probably don't go looking up the answers to.
But it is, these are all things that
Right.
you need to look for.
Yeah.
Right. So to answer your first question, did I tell the students, or did the instructor tell the students? I have to think for a second. And so what I did with this is I actually went into the classroom on the first day of class, and I introduced myself because I was going to be observing one of the classes, and this was going to be. I kind of forewarned the students so they knew that they were going to be part of a pilot, but not. I didn't term it that way. I didn't want to say you're going to be a guinea pig. But I'm going to say, I'm going to be in your classroom. I'll be visiting you. So the students were, they were forewarned, but I didn't tell them. I didn't personally tell them that I'm going to do this, this, and this, but I think the instructor of the lab, some of them would say, I didn't even want to say the term research because it wasn't, but I think sometimes the instructor expressed it a little differently. Because that wasn't a great question to whether or not this was like, okay, you're going to see this again. And I don't think that was warned to them. So for the precipitation, I'm going to go over just the laboratory exercise, mainly because this lab was very different than the lab that it eventually, it didn't, I wouldn't say use the word replaced. This lab got inserted, and another lab that was a little bit unrelated got thrown out of the lab lineup. And so in this lab, this was actually became the lab that is the first lab the students do for the class, And during this lab, the students spray water through a distrometer, and they take the data, and it's actually, I'm going like this because it's a data stick. They stick it to their computer, they see this data, and they are able to look at the fall velocities of the drops and the drop size. And they also plot radar reflectivity and rainfall rate data in Microsoft Excel. And that might seem very basic, but this was their first, like they had to show the lab instructor that they can do Excel. Hopefully it's not much of a issue as, like when I first started the lab, there was a lot of students who didn't use Excel yet, and I think nowadays, coming out of high school, a lot of students have experience with Excel. So that's what this entailed. And this is to show that there's totally different objectives here. So the new lab was looking at rain and precipitation. The old lab was actually looking at clouds, making cloud observations and relating that to what the radar and satellite images said for that day. So it's really different. I gave the students a pre and a post assessment. The assessment had some questions relating to clouds, some questions relating to precipitation. There's data that I analyzed so we can look at it, but I don't think that's something that's really, worth looking at in this presentation. But another thing to look at would be the student rating of the lab. Same question, please rate the lab 1 to 5, and the new lab was rated 3.62, and the old lab was rated 3.31. So I'll just do a brief discussion. So I think from this process, some of the successes, we incorporated professor experience with the TA teaching suggestions. So there's this team-based approach that, could have gone, at times I was like, this is not going to go anywhere. But it actually, we got somewhere, so I was pretty happy about that. Students rate the new labs higher than the old. There are higher levels of inquiry in these labs. This is kind of a subjective statement based on what I know, but also based on how we develop the lab. And it involves these real instruments and real data, which is, the main goal of the whole thing. We got this grant. Professors spent a lot of money on the instruments, and then the education piece. Let's actually use these instruments for what we wrote the grant for. So roadblocks. Now this is an issue. These labs at this time don't stand alone. We have to have somebody come in and kind of babysit the instruments throughout the entire week of laboratories. So I would love suggestions as to how we can manage this, because those instruments that we have are $3,000 per geometer, so they're expensive, and we don't have that many of them. I think you can build one cheaply, but these things, lab equipment is going to break in these undergraduate labs. Okay, another roadblock was the assessment, which we already talked a little bit about, and then shifting roles. The professor who was the instructor who was, the lecturer who was in charge of the lab retired, and then last semester there was a substitute lecturer, and then, I know that sounds a little odd, and then now there's a new lecturer who just got hired on, who's taking over this role. So we'll see what this instructor wants to do with this lab moving forward, and perhaps the lab might be tedious because of bullet point number 1. So
I have a question. Does anybody in ATOC care whether people learn this stuff?
I think so.
Do they actually have a real interest? These people don't go work in their labs or things like that, most of them.
Right. So do the professors care if the students learn or not? I actually do think the professors do care. I think ATOC, before I came on, had a history of just working on research and focusing on the research side of things rather than the education side. But since I've been here, a lot of younger, new professors have been hired, and they are doing a great job with working on science education. I'm actually pretty happy to be a part of that and see what they're doing. For example, we want to be part of the LA program, and so Baylor Fox Kemper has actually, last semester, established this quasi-LA thing before he could actually implement it and become part of it. So they are working on it.
4 courses that will have LAs this fall.
Yeah. And so that's he was a new professor after I started. He started after me. So And then Katja Friedrich, the professor who was on this grant as well, wrote, I guess, she wrote a grant to the SEI. She wrote another a Type 2 award for the CCLI. We unfortunately didn't win the SEI because I was competing against all the great departments here, but it's definitely. But it definitely shows that it was a priority within the department. Because I'm involved in science education and kind of like this own person, a grad student that does this within the department, I've sat in on some of those meetings. I have my own responsibility, so I couldn't take, too much on with the SEI, but it definitely knew that a lot of the other professors were like, yes, this is a priority, we want to do it. And it's really coming from some of the younger professors in the department.
Well, it's also a relatively young department as STEM departments on this campus go.
Yeah.
Maybe 10 years old or so, thereabouts?
Yeah, probably. Like the program, I don't really know how old the program is, so you might know better than me.
Yeah, because there was prior to APOC, there was something called PAOS, Program in Atmospheric Oceanic Sciences, and then that grew up, matured into an actual department.
Right.
But then before PAOS, there was nothing.
Okay.
So.
Yeah, I didn't know what was happening before there was PAOS. I knew that PAOS happened, and then they became their own department in 2005.
Well, historically, going way back, when the state legislature or CCHE decided which universities were going to specialize in which areas, atmospheric science got assigned to CSU in that way as part of the general. I guess it was seen as being more closely related to agriculture.
Oh,
And
interesting.
so the atmospheric science program at CSU is very old and very well established.
Right.
The atmospheric science program at CU is much younger.
Right.
I think a lot of it is a result of cooperation through organizations like CU's eventually brought up. But
Exactly.
the net result of it is you've got a relatively young department with a lot of young people in it, and those departments tend to spend more time thinking and talking about what is our discipline, what is our future, compared to sort of more established departments that tend to spend more time worrying about less interesting stuff. So,
Yeah, I think those conversations definitely have a way. They do occur. I'm not really, at this point in my life, I'm not really a part of those. But yeah, I definitely think they go through some of those growing pains. It's interesting with CSU. I mean, okay, I'll just say it. Like, because the last time I did a presentation here. I did a presentation on student understanding of climate change, and so in my department, it's very most because you still have some of those, like scientists who see it a different way, I guess, than the IPCC. I guess I'll put it that way.
I know what you're talking about.
And so I think CU is very much in line with the University of Colorado Atmospheric Science Department is very much in line with the IPCC.
Well, but just sort of backing away from that, putting in more general terms, I think. Now, I'm stating my opinion, okay? But there is a general trend for sciences, I think, in history to begin as largely empirical, and then later on develop a theoretical structure. And so, like with physics, the theoretical infrastructure was built by Galileo and Newton and Kepler. It goes way back.
Yeah.
Chemistry was much more empirical and didn't really develop theory until the 20th century. And the earth sciences, I think, in our lifetime, my lifetime anyway, have been going through that transition from being very empirical, lots and lots of collecting data and establishing patterns and finding out what the questions were, and now we're moved more towards being really based on theory and modeling. And now my opinion is that CSU, because it's an older program, has more of the empirical observations
probably much more valid than what I have to say.
I spent a lot of time watching these things, so.
Yeah, I definitely, but my dissertation research is climate change understanding, and I see, like that's part of the thing, interesting thing is that climate change, when you look at students learning climate change, I think scientists are learning climate change at the same time, some aspects of it. So you're teaching directly, sometimes the stuff that gets discovered or put on papers gets into the classroom pretty soon after that, and so there's a little bit of it's how do you expect a student, undergraduate student, to like interpret some of these nuances when scientists are not how do you expect, but it's hard to translate it from the science into the student, and I think that's still being established as well. So this is my final slide. Moving forward, hope to implement Skywatch into higher level courses and make this exercises standalone, and then continue to revise the ATOC 1070 curriculum. And one cool thing I do like about Skywatch is that you can, it records a video all the time, so there's live video being recorded, and so this is pretty cool to show what's going on in the sky if for some reason you forgot what was going on outside at that specific time, at a specific day. And so as you can see, like as it gets closer to afternoon, then you get the clouds rolling in, it starts to rain. And so this is definitely going to impact the measurements that these instruments are recording. And so they have this this thing has this for every single day. And then there's people working on it, as you can